Oh, okay. Let's look at this.
I think I'm missing it.
Before you turn it on?
I did turn it on though beforehand.
Okay. How are you doing? Oh, it looks perfect.
Good. So I didn't have a 1K potentiometer. We just had that one.
5K is fine
5K,
because
yeah.
all you need to do is be able to make sure you get through the range.
Right. Okay.
And I was plugging this into here, and then I was trying to measure the potentiometer.
Okay, you have to pull it out to measure the potentiometer. It should not be connected to your circuit.
Oh, sorry. I shouldn't do that. But I definitely.
When I teach circuits in a flipped or blended class style, I take every third or fourth class period and devote it to in-class labs. Students bring in their own devices and work right at their desks. The lab topics are chosen to be ones that are hard to understand by theory alone, such as second-order circuits, an RLC circuit, for example, that displays overdamped, critically damped, and underdamped behavior. The classroom atmosphere is engaged, with students working together and with the instructor. So, what is this?
That's underdamped.
Okay, and if you turn it the other way.
Then it goes to overdamped where it is smoother.
Right, so that's overdamped. Now, is this a higher or lower value of R?
That is a higher value.
Higher value of R, okay. Learning by failure is one of the key elements of the laboratory experience.
This is our minimum value. This is our maximum value.
Now, wait a second.
No. Wait.
That's your maximum value?
Yeah.
All right, it should be
Right?
a lot more dramatic than that.
Uh-oh.
Now, why is it you have this? Why
It's
is this
just
here?
in so that, because I couldn't get the legs of the potentiometer to stretch.
Okay, now.
Oh my goodness. Okay.
Another key element of the laboratory experience is to compare theory with experiments. So we have students do a pre-lab before class where they work out a problem analytically and then they compare the results with their experiment. And we also ask them to make predictions of the sort of behavior that they expect to see.
For our prediction, we got 245 ohms. And when we measured it, we had about 200 ohms.
That's pretty good because that's,
that's
you know,
nice.
that's about as close as you can get from.
Yeah, you're just
Okay.
Is it correct to say that when the frequency decreases because the period increases, the waveform looks more like a square wave?
Exactly, yeah. We introduce students to some practical issues that deviate from the basic theory. For example, this RLC circuit with a potentiometer in there should be run without a problem by theory. But the problem is that most function generators may not be able to generate enough current to be able to drive this circuit. So we introduce this op-amp, which doesn't change the voltage level here, but gives it enough power. So this is what they learn in class. This is what they have to build. So let's take a look at what the circuit looks like with the op-amp in it. So this circuit right here. Here you'll see the input to the circuit is a square wave, and this is the output, which is the voltage across the capacitor. Now this is the response of this circuit when I run it exactly like this without the op-amp in there. The function generator just can't provide enough current to drive this circuit.
And when we're underdamped, the system is being at underdamped, that's crazy thing happens. So we don't know
Crazy
how to put
thing,
that in.
yeah, I like that. Crazy thing happens.
So we don't know how to put that in words. So like input, I think it's like something's going backwards.
That's a good point. As you're decreasing that resistance, what do you think is happening to the current that you're trying to draw?
It's getting bigger.
It's getting bigger. So the current's getting bigger with a small r, and you just can't.
So that's why you need the op-amp to
That's why
increase the.
Yeah. Integrating experiments into a classroom setting really engages students and enhances learning. Okay, now.
Oh my goodness. Okay. That makes a lot of sense.